again, you've now learned everything for this unit. We just are going to just keep doing different types of the same examples and seeing different kind of graphs that appear. But these steps for graphing rational functions, this is it. This is all we need to do. So, if we were going to graph, right, for the graph of each function, we'll determine any non-permissible values. Well, that's going to be step 2, because that figures out if we have holes or vertical asymptotes. Then we figure out our horizontal asymptotes. That's step 3. Figure out, is there horizontal asymptotes or oblique asymptotes? Draw your graph with those asymptotes, and then finish your graph by finding intercepts and nice points and drawing it towards. That's the steps every single time. What makes this unit challenging at the beginning is that, look at the graphs we've done. That one looked like this. This one looks completely different than that one. Our first one just had a straight line with a hole in it. Right? The graphs look completely different, but the steps are the same. But the steps have a lot of stuff involved in them. Usually, when you have the same steps, you sort of see the same thing happening over and over again. Like when we studied logs, solving exponential equations, you took the log of both sides. Basically, the same thing sort of happened every single time until you got till the end. But now the graphs are looking quite different, so it's kind of interesting that way. Okay, so let's start. We always start by factoring. The bottom is the difference of squares. X plus 2, x minus 2. Can I state my non-permissible values? Absolutely. X can't equal minus 2, and x can't equal 2. And those non-permissible values will either be holes or vertical asymptotes. And what do you think, this one? Vertical asymptotes or holes? Or one of each? If they don't cancel out and go away, if your non-permissible value doesn't disappear, we don't have to rewrite the equation as I did in the note in green here. They will always be vertical asymptotes. Okay, next. Is this a situation where we have an oblique asymptote? No. Oblique asymptote is when the degree is bigger on the top after you simplify. Here we have the degree bigger on the bottom, right? The x squared is on the bottom and x on the top. I think this is the easiest one, because when it's bigger on the bottom, you'll always have a horizontal asymptote at y equals 0. And after I've got all of my asymptotes, this is where I start to graph. So vertical asymptote at 2 and negative 2. And a horizontal asymptote at y equals 0. Label all your intercepts. So y-intercept, that's the easiest one. You plug in 0 for x, and you will get 1. X-intercept, look at your numerator. Could your numerator ever equal 0? Yes. when x is 4. Once again, we have this weird situation where we have a point on our asymptote. So we're going to have to do a little bit more work, definitely, to figure out what's happening there. Okay. We have how many sections? Our vertical asymptote separated our graph into 3 sections. Look at section 1. Do you have any points in section 1? No. So because we have no points in section 1, pick a value of x in section 1. I like to pick something nearest the asymptote. And I'm going to do, again, I'll take out that orange pen, and I'll do my mental math with plugging in -3. Do you see the top would be? Oh, that's not orange. Try that again. That would be -7. If I plugged in -3 into my first one. -3 plus 2, -1. -3 minus 2, -5. And so all those negatives will mean that fraction stays negative in the end, and I'll have -7/5. So I go to my graph, I label -3, -7/5, and I have enough information to finish that section. Section 2. Do you have a point? Yes. Is it enough to draw your graph? It actually is. In this situation, because the question is, oh, should I go up or should I go down towards the asymptotes? And in this section, you have to go up, because if you went down, do you see that you would make new x-intercepts? And you've already found the only x-intercept that exists is at 4, 0. So that's a very important kind of concept that you can't make. When you found your x-intercepts, you found them all. And so you can't create any more. So we have enough in that section. Section 3, we have a point, but this one is really not very helpful because it's right on the asymptote. You don't know if things go up or if they go down and how this works. So I'm going to get another nice point. I'm going to go right close. I'm going to plug in 3. And I'm going to go back to my orange here and do my mental math. If I plugged in 3, you see the top would be -1. 3 plus 2 would be 5. 3 minus 2 would be 1. And we would get -1/5. So I go to my graph and I can label 3, -1/5. So that tells me this part has to go down towards that asymptote. Now, what happens after 4? This is kind of strange because we've got an asymptote there. So if I don't know, again, I might plug in 5. Get another nice point. What happens if I plug in 5? I'll go to my orange. Do some mental math. If I plug in 5, that'll be 1. 5 plus 2 is 7. 5 minus 2 is 3. I get 1/21. I know I call these nice points, but like you look at them and you're like, that's not a very nice point. But it's not hard to find. You can always plug things in. So 5, 1/21, well, that's just slightly above. And what's going to happen on this graph is it comes above, but then it has to go back towards that asymptote again. I don't know how high above it, like maybe it goes higher and then comes back down, but the asymptote says that's what's going to happen at my end behavior. It is going to approach there again. So again, here we have a situation where we just got a graph that's completely different than any graph we've ever seen before. but the steps stay the same. You get your asymptotes. You know that your graph is going to have to go towards your asymptotes. You find your intercepts. X-intercepts in particular are very important because you can't make new ones after you've found them all. And then you just start drawing your graph, and wherever you can't draw your graph, just plug in a value to get another point. It's actually using the graphing strategy that you first learned back in grade 9, which is make a table of values, find a bunch of points, and the more points you have, the more accurate your graph is going to get. All right, let's look at B. Well, there's a B. X squared minus 4, x squared minus 9. This can be factored. Top is a difference of squares. And the bottom is a difference of squares. Can't divide by 0, so your non-permissible values. X can't equal -3. And x can't equal 3. Does anything simplify? No. So if a non-permissible value does not simplify away, it will always be a vertical asymptote. This is a situation where you have the same power on the top and the bottom. So I'm going to rewrite my equation here. The original one was this, right? And my highest power, or my highest degree, is an x squared with the exponent of 2. So my horizontal asymptote is just going to look at 1x squared divided by 1x squared. That simplifies to 1. That's my horizontal asymptote. So I go to start my graph. Vertical asymptotes at -3 and 3. And a horizontal asymptote at y equals 1. Y-intercept is always easiest to start with. Right, I would look at my original equation. What's highlighted there, those x squareds will be 0, -4 over -9. That makes 4 ninths. So I have the point 0, 4 ninths. X-intercepts. If you plug in y equals 0, the only way a fraction is equal to 0 is if your numerator is equal to 0. So your x-intercepts from that factored form are easy to see at -2, 0 and 2, 0. We look at our graph. There are 3 sections that we have to graph because of our vertical asymptotes. Do we have any points in section 1? No. So we need a point in section 1. Pick an x value. I'm going to go with -4. And take out my orange pen. Ooh. Now, I don't know. What's easier for you here? The original equation is actually quite simple to use. Can you see if you plug in -4, you'd get 16 minus 4, 12 on the top, and 16 minus 9, 7 on the bottom. I might use the original equation here to plug it in. The factored one wouldn't be hard, but this is pretty easy. And there's something about the original one that I really like, I'm going to talk to you about in a second as well. So I get 12 over 7. So I go to my graph. 12 over 7 bigger than 1? It is. That's important that you estimate where it is correctly. That's enough to draw this section. Do we have enough in section 2? Technically, yes. I mean, there's a possibility it could bounce off that and go up. But since the multiplicity of each of these is 1, it does have to go straight through. So I would be okay if you didn't do any other nice points and drew that section. And then we have no points in section 3, so I'm going to plug in 4. And what's really nice about plugging in 4 is you see that when you plugged in -4, they're both getting squared, which makes positive 16. I don't even have to do the mental math here. I know this is also going to be 12 over 7. So I go to label that point. And our graph is done. All right, circle questions 9 and 10.